Hello, everyone, and welcome to day 3 of RailsConf. Right? And welcome to my talk today. I'm really happy that you all came to my talk. It's always nice to see the people who actually are attending the things that I want to talk about. My talk today is entitled Off to the Races. This is going to be an introduction to race conditions, general strategies that you can use if you've encountered them, a little bit of how to test them, and what I'm hoping that you'd leave with is a good understanding of what race conditions are. You'll be able to talk to the people around you and start building some of the experience so you can notice race conditions out in the wild and how you can fix them. A little bit about myself. My name is Kyle D'Oliveira, and I'm a principal software engineer based out of Vancouver, Canada. I've been working with Ruby for almost my entire career. I've worked on every single Rails version, including Rails 0. I think my first project was to upgrade from Rails 0 to Rails 3. That was a weird delight. I find the Rails inspiring. I find it empowering. I love the community, and it's one of the biggest reasons why I stay working with Rails and why I'm going to continue to stay working with Rails is because of all of you. I have been working at AHA for the past 2.5 years, and it's also one of the best workplaces I've been able to be a part of. They really do focus a lot on the employees and the human element of it, and we can help other companies build what matters for them. And the big thing I find is that the team is amazing. We're fully distributed all over the world. We have people all over the States, in New Zealand, in Europe. And the culture is great. We run with something we call TRM, the responsive method, which is just a big framework of shared values that we can all agree on, that we can agree that we'll all be interrupter-driven, we can make decisions, we can have goals, but we can also be kind about it. It helps us move quickly, be empowered, and if you'd like to be part of this culture too, come chat with me afterwards. We're always looking for new talent. Okay. So when I started prepping this talk and telling people that it was about race conditions, I had people asking me how programming had anything to do with races. And I think without any prior knowledge, the phrase race condition isn't really clear. And so I went on a little bit of a hunt for a definition, and I came up with this, which was probably the best one, which is that race conditions are unanticipated behavior caused by multiple processes interacting with shared resources in a different order than expected. Okay, that's a mouthful. And I think if I was learning about race conditions for the first time and I read this, I still would have no idea what it's trying to say. And in fact, I know about race conditions and I read this and I'm like, I'm not 100% sure what we're really talking about. So I think it might help to look at an example. And I first learned about race conditions back in university, where they introduced it to us with a problem that they referred to as the dining philosophers. And I thought we could just go through this problem together. The dining philosophers problem looks something like this. You've got a table, and around the table sits 5 philosophers. I'm not really sure why they always go with 5 rather than 2. It would be much easier, but this is typically how the problem is phrased, so we'll continue it here. And then each philosopher has some food that's in front of them, and there are 5 chopsticks that are placed on the table in between the pairs of philosophers. And there's some rules that say there's only 1 chopstick between pairs of philosophers. They can only eat if they have both of the adjacent chopsticks. And obviously, chopsticks can't be shared. They can only be used by 1 philosopher at a time. And the problem is this: what is a process that all of the philosophers can agree to so that no one will starve? It's a little bit morbid. And the process that they're actually referring to here is just like an algorithm. Is there an algorithm? And one such algorithm or process might look like this, where it's a step-by-step instruction guide for each philosopher to follow. They can reach out and they can pick up the left one. If it's not available, they can wait, and they do the same for the right. When they have both, they can eat as long as they want, and then one by one they put it down and repeat. And if you look at this and you think in theory, it might look like this. You look at a philosopher, goes out and grabs the left chopstick, and then it goes out and grabs the right chopstick and eats as much as they would like. And then they put the left chopstick down, and then the right chopstick down, and then they repeat. Unfortunately, because the philosophers are all acting independently, in practice, it might look something like this, where philosopher 1 reaches out to pick up the left chopstick. But at the same time, the second philosopher reaches out and picks up the left chopstick. And then the third philosopher reaches out and grabs the left, and the fourth, and the fifth. And unfortunately now, everyone has picked up their left chopstick, so when the first philosopher reaches out to try to pick up the right chopstick, it's not available, and they'll wait, and they'll all end up waiting. And because we haven't told them to put it back down, they're all fortunately going to all end up starving. Well, the dining philosophers is a pretty abstract problem, but it does outline some of the basics of what shows up in a race condition. Remember that complicated definition from earlier? Well, we have multiple processes here. Those are the philosophers. They're all acting independently. And we have some shared resources. These are the chopsticks. And there are some unusual timing things that can create unanticipated behavior. There's also one additional definition I'd like to point out here, which is referred to as the critical section of the code or the algorithm. And this is the section of the algorithm where the philosophers first reach out for the shared resource up until the point where they stop using that shared resource. Okay, so understanding philosophers and how they dine is great. But this is Rails conference, and typically there's not going to be philosophers or chopsticks in your Rails apps. But there's definitely going to be multiple processes. There's going to be concurrent requests. If you are a Rails app that serves one request at a time, you're probably not doing a good job. There's background jobs that could be running at the same time that could also be interfering with things. There are rake tasks that could be running through like a cron task or something like that. And these are all going to be interacting with shared resources. You likely have a database. That's a big shared resource. You could be using something like Redis or even other microservices. If I had to guess, I would say almost every commercial Rails app uses shared resources and has multiple processes. So unfortunately, the possibility of race conditions in Rails code is always going to be present. So here's a really simple example of what code that is vulnerable to a race condition might look like. Imagine that we had an app that created ideas and you could vote on those ideas. We have an idea controller here with a vote action. And let's walk through this. Imagine a request comes into this action. We could look up that idea with the ID. And let's say it had 0 votes. We increment the vote counter and then save it to the database. And in the database, we have 1 vote. Then the next request comes in and it does the same thing. It loads up the idea, increments the votes, saves it to the database. We have 2 votes. Great. But what would happen if the timing of this was slightly different? Imagine just like before, a request comes in and we load up the idea and that vote counter is incremented. But at the same time that vote counter is incremented, a new request comes in and it loads up that idea from the database just before the first one saves it. Now, the first request will save the votes, we'll have 1, and when the second request goes through and increments the vote counter and saves it, we are also left with 1. That's a little bit confusing. What happened to this vote? Let's go through this one more time with a little bit more detail. The first request comes in, and it loads up the idea. This goes to the database and extracts that idea, and it creates an in-memory representation of that object with 0 votes. We then increment that object's vote counter by 1. And this is where the second request comes in, and it goes to the database and does the exact same query and loads up an in-object or in-memory representation of that object with also 0 votes because it has not yet been persisted to the database. The first request will then go to save it and update the idea and tell the database that there is 1 vote. And then when the second request gets there, it ends up issuing the same update, saying that you need to update the votes to be 1 again. And this is where we end up losing that vote. This is an example of what's known as a read, modify, write style race condition. It's a common enough pattern that they've given it a name. And so if you have places in your code where you read something, you modify it in memory, and then write it, which probably happens very significantly, this could result in a race condition if there was a conflict in the database at the same time. Let's say you suspect that your code has a race condition. How could you go about testing? It can be pretty tricky to test race conditions. By their very definition, they're non-deterministic, and they often require very specific timing in order to be triggered. The first thing you could do is look to identify the critical section. This typically starts the first time you reach out for a shared resource up until you finish with that resource. So in this example, these 3 lines could be viewed as the critical section. And one option you could do, which should be pretty straightforward, is to try to increase the definition or increase the duration of the critical section. And you could do this with a pretty simplistic sleep. This could reduce the timing restrictions required to reproduce the race condition, but it's not great because you do still need to make sure you hit the second request at the same time. The second request is also going to sleep. One thing you could do is you could do a little helper method or service that does something a little bit more clever, like this. With this code, you could use a shared service like Redis to do something like set a flag if it doesn't yet exist in Redis. And if you were successful in setting that flag, just sleep, and you can sleep indefinitely. Now, if another process comes in and doesn't set the flag, just have it delete the flag. And what this will end up looking like is a request will come in, it will see that there is no flag, and it will just kind of get stuck in the sleep loop, and it will just wait. It will wait there indefinitely. And when the second request comes in, it will see that the flag is there, delete the flag, and then they both fall through together. This is a pretty simple technique, but it can actually give you some pretty reliable ways to have 2 processes hit the same area of code at roughly the same time, which is typically key for race conditions. So in this case, we can guarantee that they both loaded the idea into memory before persisting, so we could pretty reliably reproduce this race condition. We could also go down the path of creating some automated testing for race conditions. It's great if you've been able to reproduce it and want to try to set up some sort of TDD approach when it comes to fixing it, or just to prove to yourself that it does exist. However, tests are often single-threaded, and that is a problem. When in other environments like development, you can make multiple requests, you can have multiple jobs running, but how do you test a problem that only shows up in multiple processes when you inherently only have one process? You'll need to figure out how to mimic the idea of a race condition within a single process. And there's a really amazing, I think, often underutilized method that comes from RSpec mocks, if you're using RSpec, that can help with this. And this method is called andWrapOriginal. And what this allows you to do is to stub a method. For instance, we're going to look to stub the find method on ideas. And you can do something before or after, but continue to leave everything else as it is. Now, some people are adverse to mocking, but what you're trying to do is you're not trying to change the behavior of the code. You're trying to kind of inject something into the background. And this means you can call that method exactly as it was and return exactly what this method would have returned, but then do something in the middle, like this. And with something like this, you can ensure that you've loaded the idea out of memory, and the moment you've loaded it out of memory, you've modified the database in the background, so this idea is now out of date. And so you can do some testing with it. And a test could look something like this. You could create an idea, use that little trick with andWrapOriginal, make a post, and then expect that the votes are going to be 2. And with the code that we have, this test will fail. Now, this is not a silver bullet for testing. it can be pretty tricky to figure out what method do you need to kind of stub in order to kind of mimic this process. So it does require the ability to dig into the code and be able to extract that. And even if you do fix it or find it, fixing the race condition doesn't necessarily mean you're going to end up fixing the test. And I'll go through that a little bit more why in the future, but this is a useful tool to have in your toolbox. So we've talked about testing. Let's talk about how to fix them. Once you have found a race condition, how do you deal with it? And there are a few different approaches, but no silver bullets. So it's good to think about the approaches and how could they apply to your problem. The first, and hopefully the most obvious way you can fix it, is just to remove the critical section. And I don't really mean deleting the code, but you could refactor the code, so maybe it doesn't have it. But you can't always do that. One thing you can do, in some cases, is to see if you can perform some sort of atomic operation. An atomic operation is an operation that's just executed as a single unit. In other words, there's no other process that can read or modify pieces of it while that operation is running. So in this case, rather than load up the idea, increment the vote, and persist it back to the database, you could tell the database to perform the increment. Rather than SQL that looks like this, where the database is being told what the vote should be, the database is being told how to perform the update and to set the votes to one more than whatever it is currently. Because it isn't loading the object into memory, and because this operation is atomic, we don't have a race condition here. So if there is an atomic operation for what you're dealing with, this might be an ideal approach. However, that's not always possible. And this is not limited just to the database. This could show up in other services too, like Redis. This code is vulnerable to exactly the same race condition. What would happen if another process were to update the count between the time it was get and the time that it was set? This is the read, modify, write problem. So instead, whenever you see something like this, you can look to see if you can combine it into a single statement. For instance, Redis has an increment command that is atomic, and so you can use this command to remove the race condition. The type of atomic action or operation that you'll use will change based off the issue you're looking at, so it's good to start trying to understand what atomic actions exist. However, if you can't make the operation atomic, you might need to take a different approach. One approach you could take is to try to detect that a race condition happened and recover from it. There's many ways to do this, and they can all be different based off the problem that you're looking at, but one interesting thing that Rails supports is something called optimistic locking. Using this, Rails will only apply an update to the database if it's the same version of the object that you had in memory. To enable optimistic locking, it's pretty easy. All you need to do is add a lock version column to your table, and Rails will immediately pick it up and start using optimistic locking. And with that column in place, Rails will change the SQL that is performed to something like this. So instead of just setting the votes to be 1, it will also update the lock version field whenever something changes. But in particular, it will only apply this update if the lock version is the same version as the object that it was in memory. Now, this technique with optimistic locking can be a little bit dangerous because you may be silently ignoring updates, which could be really undesirable. So you want to make sure that you're using like the save exclamation mark style methods. And in this case, if it doesn't update anything, you'll get an exception with this active record stale object error, and you can do something with this. You've now detected that someone has changed this idea out from underneath you, and you can take the appropriate action. And in this case, you could retry. That could be an acceptable action. You do need to ask yourself a few questions, though, like how many times would you want to retry? You don't want to get stuck in a loop where you're just retrying over and over and over. So at what point in time are you just going to say this is not successful? How do you handle that error? Those are good questions for you to ask. There's also one really important note with this style of approach, and is that all of the changes that you do within the critical section, if you're retrying, need to be able to be undone on failure. With a database transaction, which I'm hoping all of you use, this could be really simple. You issue a rollback, you're good. But there are some external side effects that are much harder to undo. What if you made a third-party API request? What if you queued a background job? What if you sent an email? Those are all very difficult to undo. So in those cases, if this is something that you're doing, this style of approach may not be appropriate. And depending on how many times you are willing to retry, this could also end up with a lot of thrashing, where processes are constantly performing the changes, undoing the changes, performing them again, and just kind of stuck in this cycle. So if you're unable to detect and recover, or it's really complicated to do so, you can look to protect the critical section. And this is a common way of dealing with race conditions. And what you're trying to do is you're trying to set up a bit of a contract within your code, basically saying anywhere that these shared resources are being used in a way that conflicts, they need to all be protected in the same manner. Just like Rails supports optimistic locking, Rails supports pessimistic locking. This is one way that Rails offers to protect the critical section. With pessimistic locking, a process is telling the database that once you've extracted an object from the database, only it has access to it until a transaction is completed. To utilize pessimistic locking in Rails, you could do two things. Firstly, make sure your code is wrapped in a transaction. And secondly, when you go to look up the idea, you can provide the lock method. And instead of issuing a typical SQL select statement, it will issue a select statement with some extra information telling the database that this is for an update, so lock this row. And then you can continue to execute your code as normal. At the end of the transaction, the database will remove that lock and the critical section is open again for business. And to tie this a little bit into the theme of race conditions, you can kind of view this lock as a baton pass. In a baton race, only one person can run, and that's the person who has the baton. You can't really run the race while you're not holding it. And this is what the lock kind of represents. The code can't run at all until it obtains the lock. And then and only then can it run. And while it's running, it's going to prevent anyone else, any other process, from running until it gives up that lock. So with a lock in place, it will protect the critical section. If two requests come in, only one of them will end up making it inside the critical section, while the other will be blocked from entering and will just have to wait outside. Similar to the detect and recover approach, this does still require you to answer some questions. And the first important question is, how long are you going to wait? Sleeping in requests and jobs is not ideal. And in fact, I'm sure if you just plopped a sleep in there and threw up a code review, someone's going to probably make a comment about it. And it often ends up leading to just lots of processing power not being utilized. You can end up having really slow requests, which your customers are going to complain about. And at some point in time, you may have waited too long. So what are you going to do if there's a timeout? If you're unable to lock specific rows, you could also look to lock arbitrary blocks of code. These are some other ways you could protect the critical section. One of them is using an algorithm such as Redlock, which is a Redis-based distributed locking implementation. And to utilize this is pretty straightforward. With this gem, you can create a new client with Redlock, and then just call the lock method with some sort of identifier and a timeout. And then inside this block, you can handle your critical section. There's another gem that's out there as well called with advisory lock, which does something very similar with advisory locks in the database. An advisory lock is just an application-defined lock. They typically need to be manually unlocked and locked and unlocked, and this gem handles that for you. And utilizing this gem looks pretty much exactly like the Redis Redlock example, where you wrap the critical section in a method call. In this case, it's called with advisory lock, and you provide some sort of identifier for the section. Remember, though, that protecting the critical section is a contract. So in order to protect the critical section, any place that increments the votes in this kind of manner would need to use the same style of lock and the same identifier. And error handling with this doesn't need to be crazy complicated. You could do something like this, where you specify a timeout, 1 second, and if it's not successful, return that error to the user. This might be sufficient for handling error cases. But one really important thing that I want to stress with protecting the critical section is to be really mindful of how long you will wait. And I don't necessarily mean what is the maximum time that you will wait, although that is an important question, but how long are you going to be waiting in aggregate? Protecting the critical section is great. It will remove some of the drawbacks of like detecting and recovering. You don't need to undo changes. You can just ensure that nothing else is infected or affected. But this technique effectively removes concurrency. And preventing access to the critical section can mean that some services are just waiting around, doing nothing. And if you put this kind of code in a really high throughput area of your code base, this could lead to an entire service looking like it's down or all the workers are busy doing nothing. So it's something to be really mindful of when you're introducing these protections. I also wanted to mention another really common kind of race condition, which is often referred to as the check, then act style race condition. And this pops up pretty frequently in various places, but in particular, it shows up in the validates uniqueness of constraint that shows up in Rails. The purpose of this validation is, like the name suggests, is to prevent duplicate data from being inserted into the database. Like in the example above, it would prevent it would make sure that the username is unique across the entire database. The second example says just, be unique for this specific account. But if you look into the documentation of validates uniqueness of, you see something that they immediately point out in that this is inherently prone to race conditions. You have one job, prevent uniqueness, and you can't prevent uniqueness. This is because the validation happens first and then the insert. So at some point in time, a process could come along and insert data in the middle. What this might actually look like in code is if you had a validates uniqueness of validation set up on your model, that means that this specific line, just this create an idea, this one line is vulnerable to a race condition. Now it's maybe a little bit difficult to see why. It's only one line. How can you do anything in the middle? But in order to see that, you actually have to dive into a little bit of the Rails internals. And in the create method, what this is really doing is it's creating a new object and then saving it. And the save option, or the save method, does something like this, where it will perform validation, and if the validations are correct, then it will persist it to the database. And the race condition in particular would look like this. If you, during the perform validations, some sort of SQL will get executed like this that will go to the database, say, are there other ideas with this name? And if it returns data, you know that there is one, and you can not persist the data. But if not, you can go ahead and save it, which will then insert the data into the database. So can you see where the race condition would need to happen? Well, right in the middle of these two statements, what if another process got there and inserted the same idea into the database? The end result would be that the validation pass saying there's no unique data, and then you try to save it and it fails because it's a conflict. So we went through how to fix some examples with the read, modify, write style. Let's go through the same examples or the same styles of fixing for how do we fix this specific kind of race condition. Just like before, one option you could look into is remove the critical section. So if we're going to create the idea, I don't think you can just simply be like, we're just not going to do this and delete this code. That's fundamentally different, completely different behavior. So that's probably not an option. But we could look for how could we make this operation atomic? One way we could do is we could swap out this create method for something that utilizes the upsert method from within Rails. And what this will do is it will change the SQL that was being run to something that looks like this, where on a conflict of the name, just do nothing. This tells the database that, like, hey, if you run into that conflict, you're fine. Just don't error, keep going. This code does not contain the race condition. But it is also still very different than the original. If you wanted validations to be run, this would not run those. If you wanted to make sure callbacks are being run, this is going to skip those callbacks. If you needed to work with this idea later on in the request, you don't have the idea. You have to go back to the database and get it. So this style of approach could work in some cases. Maybe you're trying to seed a database, but it might not work in others. So if it doesn't work, you can go down the detect and recover approach. In Rails, if an insert fails because of a unique index, it will wrap this up into an active record not unique exception. And this means we could rescue this exception and then do something. One thing that we could do is look up that idea from the database. We knew that that database existed before, or because the unique validation failed, so we can extract it and continue on potentially. Maybe we don't need to do any other kind of retrying here. If all you cared about was that there was an idea with this name, this might work completely fine. Or this is also different. If you're always expecting a brand new idea to be created, this might not be appropriate, and maybe you need to return an error to the user. So if we didn't want to do that, one thing you could look for is how could you protect the critical section? And we could reach for some of the tools that we talked about. So for instance, you could lean into something like with advisory lock. And with this lock, we can ensure that only one process was in this critical section of creating this idea. You need to make sure that the identifier, though, maps the name somehow as input for the identifier so that you can concurrently create ideas with different names, and only the ideas with the same name are the ones that are prevented from conflicting. Remember, though, that this is the contract, so you'll need to find every place that you're potentially creating ideas and protect them in the same way, which may not be feasible. I'd like to kind of finish this talk with a little flowchart that I'll leave up on the screen so people can either take photos of it, and the slides will be available later, of some general thought process when approaching race conditions. The first question you can always ask yourself is, am I working with shared resources that could conflict? And if the answer is no, don't worry about it. And are there multiple processes that are going to be working on the shared resources at the same time? If not, you're fine. But probably within Rails, you're dealing with database, multiple requests, you're probably going to be the answer is yes. And this is the hardest question. Is there a race condition? And this is a pretty complex question. You can look for some patterns like the read, modify, write, check, then act. There are others. There's deadlocks, live locks. There's a lot of different styles of race conditions that can show up, and it takes experience to be able to look at those, understand, could this be a race condition, and kind of internalize that. This is things that you could go start figuring out within your organization. Start building a list of what could help people, so if someone new joins, they can get up to speed quickly on what potential race conditions can show up. If you don't have race conditions, you're done. But if you do, the first question you can ask is, how do you remove the critical section? One way is you can actually remove or refactor the code if that makes sense. But if you can't do that, can you do something to make the operation atomic? There's many atomic operations that exist out there. The databases can do various things. Redis can, for instance, pop something off a list, and it's not going to be, that is an atomic action. You can go through the list and try to find, like, what are the atomic actions that exist, and start trying to see what could apply where. If you can fix this, great. And if not, can you detect and recover from this race condition? You can use techniques like optimistic locking. You could use the exceptions that Rails returns for unique violations. And if you do, what are you going to do with that? Are you going to retry? How many times do you need to retry? What do you do on error? And if you can't protect the critical section, or if you can't detect it, can you protect it? And you can use all sorts of different ways to do this. Pessimistic locking. You can use red lock. You can use with advisory lock. You can create your own service style lock where you can lock arbitrary blocks of code to make sure that the critical sections are protected. But you need to ask yourself, how long is this going to wait? How long is the maximum? How long is this going to wait in general? What do you do when this exceeds that? And if all of these answers are no, then you might have to look for a very application-specific solution. Maybe you're dealing with some sort of distributed system, and you need to figure out how to perform race conditions across two systems. And this could be very application-specific. You could also go back to seeing if you could refactor things and remove things that way. I'll leave this up here for now. And that's actually all I have for you today. I have some time now if anybody has any questions about race conditions. So the question is, what is some of the things that I have found for myself? So in general with waiting, waiting for longer than a couple seconds is typically bad. If you are checking something that's really high throughput, what you can also do is then be like, okay, instead of waiting, my error condition is maybe I'll spin up a background job that will try this again in 5 minutes. And that is sometimes not enough to kick it out far enough in the future that we're not utilizing the process to wait. We're just going to schedule it and it's going to try later. There are some general patterns for race conditions that you can start noticing. Like, okay, if you do see something that's like, I'm going to increment this in memory and save it, like those should be like triggers to be like, this is going to be bad. If you read something out of like a list of data in Redis and then remove stuff, well, you're doing something where you're checking and then you're doing something. You're reading and then modifying. Maybe can you do that, some sort of atomic operation? I would say like race conditions are not super, like you're not going to run into them every day, but when you run into them, they're just going to be a pain to deal with. Sure, so the question is, sometimes companies have a culture of being like, this is a race condition, we don't need to worry about this. How do you get kind of buy-in? You kind of have to get buy-in in the same way that you get buy-in from other bugs. And in particular, depending on the race condition, like try to figure out what is the consequence of it. If the consequence is like, hey, you have a customer that's sending us data, and every now and then we're just going to silently delete their data. Like if you phrase it like that, people are going to be like, that's not good. Don't delete the customer data. You'd be like, okay, so I'm going to spend some time so we don't. And you're not really deleting, you're just maybe ignoring it. And that's some ways you can get by, and is try to talk about what the consequences are. Like, is the consequence that if something bad happens, you're going to send someone 50 emails? That might not, like, they might not care until it happens to them, or you can communicate that, hey, you know what, this is going to happen to a customer, they're going to get 50 emails, they're going to cancel. And then you can actually start representing that as monetary. Also within the engineering organization, if you can show that a race condition exists and everyone's like, nah, we're not going to fix it, there is a bit of a culture thing there. What can you do to help people get on board? Are they saying we shouldn't fix this because this is hard? And if that's the case, like, they are hard to solve, but you can also be challenged solving these and learn and grow and then get better at them. We've had issues with deadlocks, and for a long time, everyone ignored them until someone championed owning deadlocks. And now there's a lot more tools or processes. Like, if you encounter a deadlock, here's a list of steps you can take to at least figure out what is happening, and we can try to figure out from there. Just here. So the question is instrumentation for knowing that you've succeeded in solving a race condition, or that it needs. Unfortunately, no, I don't have any general tactics for. Sorry, yeah, I did repeat the question, right? Yeah. So unfortunately, no, I don't have any great tactics for instrumentation for like proving that race conditions exist, because you were right. Most of the time, you will see a situation where you have like one-off event, you look into it, and you're like, oh, I think this is a race condition, but you don't know how much this has happened before. For some cases, you can start digging things in. So if, for instance, you didn't have a unique index and you've started inserting unique deduplicate data, you could actually start like querying the database and see like, how prevalent is this? Are we missing fields certain places? Do we have duplicates? And that could be value enough to show that this happens a lot. One other thing is you can do is you can start, if you suspect it, you can do the work of maybe not fix it, but do the work of like, see if you can detect it and then log it. And then maybe that can start providing more information that this is happening a lot. Yeah. Sure. So the question is, what are the trade-offs of protecting and rescuing and dealing with race conditions versus just kind of accepting the consequences? And I actually think that's a really good question because I think in some cases, you might want to, like, protecting them, fixing them can actually lead to more complicated behavior. I think the distinguishing thing that you need to factor in is what is the consequence? If you have a user on the site, they click a button and it's a failure and they get a message that just says something went wrong and they click it again, it's successful, that might not be something that you really need to complicate the code to try to figure out what's going on here. But maybe you're importing thousands of records from an external system and it dies halfway. Do you want the user to just like do the whole process again? Do you want to then try to deal with the intermediate state in the middle? That could be a situation in which you do want to make sure that like, whatever happens here, we're going to fully complete it. So look at what is the consequences of ignoring it. And sometimes that can actually justify that you are going to make the code a little bit more complicated. Sometimes you can have really nice code, but it's not even handling errors. So even starting to fix them, you can also start bringing up like, here's how to do general error handling in like across everything, which can actually just lead to actually better code in general. So the question is, have I had any success with Rubocop to find any low-hanging fruit? What my typical goal is, if I find a pattern that exists that can be really expressed with like a Rubocop rule, yeah, absolutely, let's go down that road. So the examples that I've shown were like, oh, we're going to increment something and then save it. That is something that you can start trying to get Rubocop to be aware of, particularly if you're doing something like that in Redis, because it's often really easy to be like, oh, in the Redis call, you're doing something +1. But yeah, I think it's a case-by-case basis. And for myself, I've had a little bit of success finding areas that these problems show up, and then just saying like, hey, can we just search for this problem everywhere else with some sort of static code analysis? I think this will be my last question. I would say like if you have a large transaction, sorry, the question is if you have a large transaction that's updating a lot of records, are those more vulnerable to a race condition? And I think the answer there is a little bit yes, because the longer the transaction is open, the bigger the duration of that critical section is, the more likely there's something that could conflict with it. I would say like the general rule is try to keep transactions really short, try to keep anything that you're working with lots of records. Can you do those in batches so that those are like small transactions that you can then commit? I've definitely run into issues where we're doing like, oh, like let's update the position of these 10,000 records, and 50% of the time they will fail because something has changed in the middle. Okay, thank you everyone for your time.